Astronomers now estimate there are roughly 2 trillion galaxies in the observable universe. That is a 2 followed by 12 zeros. And here is the remarkable part. About 90% of those galaxies are too faint, too small, and too distant for our telescopes to detect. When you step outside on a clear night, away from city lights, you might count a few thousand stars. Perhaps you notice the faint smudge of Andromeda if you know where to look. But everything you see with your naked eyes represents an almost incomprehensibly tiny fraction of what actually exists out there. If you started counting to that number right now, 1 digit per second, without pausing for food or sleep, you would be counting for about 63,000 years. That exceeds all of recorded human history. That stretches back before humans learned to write anything down. And that enormous figure only accounts for galaxies within the portion of the cosmos where light has had enough time since the beginning of everything to actually reach us. Beyond that boundary lies more universe, perhaps vastly more, that remains forever hidden from our instruments. Tonight, we are going to explore all of this. We will start with fundamentals, examining what a galaxy actually is and why tallying them proves so difficult. We will trace the scientific journey from earlier estimates of around 100 billion to today's figure of approximately 2 trillion. We will examine the cosmic web, the breathtaking structure connecting everything across unfathomable distances. And we will investigate the hidden majority, those countless galaxies spinning through darkness that our instruments cannot detect. So settle in, get comfortable. This will be a long journey through some of the deepest questions humans have ever asked about the cosmos we inhabit. Before we can count galaxies, we need to understand what we are actually tallying. The answer proves less straightforward than you might expect. A galaxy, at its most basic level, is a collection of stars, gas, dust, and dark matter, all bound together by gravity. That sounds simple enough. But the range of what qualifies as a galaxy is staggering. Take our own Milky Way. It contains somewhere between 100 billion and 400 billion stars. The reason we lack an exact count mirrors the challenge of counting galaxies themselves. Many of those stars hide behind clouds of gas and dust. Many are too dim to detect. We are stuck inside our galaxy, which makes accurate surveys surprisingly challenging. Imagine trying to count every tree in a forest while standing in its center, surrounded by trunks blocking your view in every direction. The Milky Way spans about 100,000 light-years across. In miles, that works out to roughly 588 quadrillion miles. If you could somehow drive a car at highway speeds from one edge to the other, the trip would take about 670 billion years. But our galaxy is actually fairly average in size. Some galaxies dwarf the Milky Way entirely. Consider IC 1101, a supergiant elliptical galaxy located about 1 billion light-years from Earth. Earlier measurements suggested IC 1101 might span 6 million light-years, but more recent studies using careful brightness measurements place its diameter closer to 400,000 to 550,000 light-years. Still enormous. You could fit several Milky Ways across it. Estimates suggest it contains somewhere around 100 trillion stars, roughly 1,000 times more than our galaxy holds. On the opposite end of the spectrum sit dwarf galaxies. These are the runts of the cosmic family, and they are incredibly common. Most galaxies throughout the cosmos are actually dwarf galaxies. Take Segue 2, a tiny dwarf galaxy orbiting the Milky Way. It contains only about 1,000 stars. Your neighborhood might have more houses than Segway 2 has stars. This galaxy is so small and so faint that astronomers only discovered it in 2009. It had been hiding in plain sight, too dim for anyone to notice. This matters for our count. When astronomers estimate around 2 trillion galaxies, a huge portion of those are tiny dwarfs like Segway 2. They are not the grand spirals decorating astronomy books. They are not the magnificent ellipticals packed with ancient red stars. They are modest collections, sometimes containing just a few thousand stars scattered throughout the universe. Now let us examine the different categories of galaxies, because this affects why counting them proves so tricky. First, there are spiral galaxies. These match what most people picture when imagining a galaxy. They feature a central bulge of older stars surrounded by graceful spiral arms filled with younger, bluer stars, gas, and dust. The Milky Way is a spiral galaxy. So is Andromeda. Spirals comprise about 60 to 70% of the large galaxies we can readily observe. Then there are elliptical galaxies. These range from nearly spherical to elongated football shapes. They contain mostly older, redder stars and very little gas or dust, meaning they produce few new stars. Elliptical galaxies span the full size range, from the smallest galaxies we know of to the absolute largest, like IC 1101. Next come lenticular galaxies. These occupy a middle ground between spirals and ellipticals. They possess a central bulge and a disk resembling a spiral galaxy, but they lack distinct spiral arms. Think of them as spirals that exhausted their gas supply and stopped birthing new stars. Finally, there are irregular galaxies. These are exactly what they sound like. They do not fit neatly into other categories. They display chaotic, undefined shapes, often because gravitational disturbance from a close encounter with another galaxy scrambled their structure. The Large Magellanic Cloud and Small Magellanic Cloud, two satellite galaxies of the Milky Way visible from the southern hemisphere, are both irregular galaxies. Here is where counting galaxies gets complicated. Where exactly do you draw the boundary between a galaxy and something that is not a galaxy? Consider globular clusters. These are dense spheres of stars, typically containing tens of thousands to millions of stars that orbit galaxies. The Milky Way has about 150 globular clusters. Are these galaxies? Most astronomers say no. They generally contain less dark matter than true galaxies. They are typically smaller, but the dividing line remains fuzzy. What about ultra-diffuse galaxies? These were discovered relatively recently, and they are strange. They can be physically large, sometimes approaching the Milky Way in diameter, but they contain remarkably few stars. They spread out so thinly and appear so faint that they are nearly invisible. An ultra-diffuse galaxy might be 99% dark matter with just a scattering of stars mixed in. Do these count toward our galaxy total? Yes, they do. But we only started finding them in significant numbers during the 2010s. And what about tidal dwarf galaxies? When two large galaxies collide, gravitational chaos can pull long streams of stars and gas out into space. Sometimes these streams condense into their own gravitationally bound structures. They become new galaxies, born from the collision of larger ones. Do we count these? The point here is that counting galaxies differs from counting marbles in a jar. There is no clean, universally agreed upon boundary between what qualifies as a galaxy and what does not. The figure of approximately 2 trillion includes many judgment calls, many assumptions, and many objects right on the borderline. For decades, when astronomers discussed how many galaxies populate the observable universe, The accepted range was somewhere between 100 billion and 200 billion. Then, in 2016, that estimate multiplied by a factor of 10. How did that happen? To understand, we need to revisit 1995 and a gamble that transformed astronomy. In late 1995, astronomers decided to attempt something that seemed almost reckless at the time. They pointed the Hubble Space Telescope at a tiny, apparently empty patch of sky and simply stared. For 10 consecutive days, they gathered light from a region of space that looked completely blank. No bright stars, no known galaxies, just darkness. The patch they selected was minuscule. If you held a tennis ball at arm's length against the night sky, the observed area was about the size of Franklin Roosevelt's eye on a dime held at the same distance. It represented roughly 1/24 millionth of the entire sky. Many astronomers thought this was squandering valuable telescope time. Hubble was and remains one of the most sought-after scientific instruments ever built. Researchers compete fiercely for observation time, and here they were, dedicating 10 days to staring at nothing. But when the data returned, what they found astounded everyone. That tiny patch of seemingly empty sky contained approximately 3,000 galaxies. 3,000 galaxies in an area so small, you would need powerful magnification to see it if drawn on paper. Some of these galaxies were so remote that their light had traveled for over 10 billion years to reach us. This image became known as the Hubble Deep Field, and it fundamentally altered our understanding of the cosmos. If that tiny random patch contained 3,000 galaxies, and the sky contains 24 million such patches, then the calculation was direct. Multiply it out, and you reach roughly 70 billion galaxies visible from Earth. Additional observations refined this figure. In 2003 and 2004, Hubble performed an even deeper observation called the Hubble Ultra Deep Field. This time, the telescope observed an even tinier patch of sky for about 11 days total. The resulting image revealed approximately 10,000 galaxies in a region about 1/13 the diameter of the full moon. Based on these observations and others, astronomers settled on an estimate between 100 billion and 200 billion galaxies in the observable universe. This range was widely accepted and repeated for years. But there was always a problem with this estimate, a significant problem. The issue was that researchers were only counting galaxies they could actually detect, and it turns out they were missing most of them. Picture trying to count how many fish inhabit the ocean, but your net only catches fish above a certain size. You drag your net through the water, count your catch, and then attempt to estimate the total fish population based on that sample. But what if 90% of fish in the ocean are too small for your net? Your estimate would be dramatically off. That was essentially happening with galaxy counts. In 2016, a team led by astronomer Christopher Consolis at the University of Nottingham published a paper that changed everything. They did not discover new galaxies. Instead, they did something clever with existing data. What Consolis and his colleagues did was analyze how galaxy numbers changed at different distances and different epochs in cosmic history. Because light requires time to travel, when we observe distant galaxies, we are also looking backward through time. A galaxy 1 billion light-years away appears to us as it looked 1 billion years ago. Their findings were striking. When the universe was younger, it contained far more galaxies than it does today. The early universe was packed with small, faint dwarf galaxies that have since merged together to form larger galaxies. This was something astronomers already understood. Galaxies merge over time. The Milky Way itself resulted from many smaller galaxies that collided and combined over billions of years. And we are not finished merging. In somewhere between 4 and 8 billion years, the Milky Way may collide with Andromeda. Recent studies suggest this collision is less certain than previously thought, with some models indicating only about a 2% probability of direct merger in the near term. But if it happens, the two will eventually merge into a single, larger galaxy. What Consolis's team recognized was that these small early galaxies were mostly invisible to us. They were too faint, too small, and too far for even Hubble to detect. When you account for all the galaxies that must have existed based on merger rates and galaxy growth over time, the number climbs dramatically. Their new estimate was approximately 2 trillion galaxies in the observable universe, 10 times higher than the previous figure. Some astronomers push back on this number. The estimate relies on mathematical modeling and extrapolation, not direct observation. No one has actually seen 2 trillion galaxies. Researchers have inferred that they must exist based on how galaxies evolve over time. But the fundamental point stands. The 100 billion to 200 billion estimate was based only on galaxies we could directly detect. It ignored all the small, faint galaxies that our telescopes cannot see. When you factor in those hidden populations, the number rises dramatically. We keep using this phrase, the observable universe. It is time to explain exactly what that means, because it represents one of the most crucial concepts in cosmology. The observable universe is not the whole universe. It is just the portion we can see. And the reason we can only see part of the universe has nothing to do with our telescopes lacking sufficient power. It has to do with the fundamental nature of light and time. Light travels at a finite speed, about 186,000 miles per second. That is fast by everyday standards. Light could circle Earth about 7.5 times in a single second. But the universe is so incredibly vast that even at that speed, light requires substantial time to travel anywhere significant. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star other than the Sun, Proxima Centauri, takes about 4 years. Light from Andromeda, the nearest large galaxy to us, takes about 2.5 million years. Now consider this. The universe has not existed forever. It had a beginning about 13.8 billion years ago in what we call the Big Bang. That means there has only been a finite amount of time for light to travel. In principle, you might think this means we can see objects up to 13.8 billion light years away, since that is how far light could travel in the age of the universe. But reality is more complicated because the universe is expanding. Space itself is stretching. Galaxies are moving farther apart from each other, not because they are traveling through space, but because the space between them is literally growing. This expansion means that light from distant objects gets stretched as it travels, and it also means that the most distant objects we can see are now much farther away than they were when they emitted the light we are receiving. When we account for this expansion, the observable universe turns out to have a diameter of about 93 billion light-years. That works out to roughly 544 sextillion miles. Everything beyond this boundary, which we call the cosmic horizon or the particle horizon, remains invisible to us, not because it does not exist, but because there simply has not been enough time since the beginning of the universe for light from those regions to reach us. And here is the truly mind-bending implication. The universe beyond our cosmic horizon almost certainly exists. In fact, most cosmological models suggest that the full universe is vastly larger than the observable portion. Some estimates suggest the full universe could be at least 250 times larger in diameter than what we can observe. Other models suggest it could be infinite. These remain hypotheses rather than confirmed facts, since by definition we cannot observe what lies beyond our horizon. When we say there are approximately 2 trillion galaxies in the observable universe, we are only counting galaxies within this cosmic horizon. We are only counting galaxies whose light has had time to reach us. How many galaxies might exist in the full universe, including the parts we cannot see? If the universe is uniform in all directions, which observations suggest it is, then regions beyond our horizon should contain roughly the same density of galaxies as the regions we can see. If the full universe is 250 times larger than the observable universe in diameter, then its volume would be about 15 million times larger. That would suggest something like 30,000 trillion galaxies in the full universe. And if the universe is infinite, then the number of galaxies would also be infinite. These figures are essentially impossible for the human mind to truly grasp. We can write them down, we can calculate with them, but we cannot really internalize what they mean on a gut level. Now, let us zoom out even further and examine how all these galaxies are arranged in space. Because they are not scattered randomly, they are organized into one of the most elegant structures in all of nature. We call it the cosmic web. When astronomers first started mapping galaxy positions in three-dimensional space, they expected to find them distributed fairly evenly. What they discovered instead was completely different. Galaxies are arranged along filaments, like threads in a spider web. These filaments connect at nodes, dense regions where thousands of galaxies cluster together. And between the filaments stretch vast empty regions called voids, where galaxies are rare or absent entirely. The overall structure resembles a sponge, or the foam of soap bubbles, or even the neural network in a brain. It is intricate and spans the entire observable universe. Let us walk through this structure, starting from where we are and zooming out gradually. We begin with the Milky Way, our home. The Milky Way is not alone in space. It belongs to a small collection of galaxies called the Local Group. The Local Group contains more than 80 galaxies that we know of, all gravitationally bound to each other. The three largest members are the Milky Way, Andromeda, and Triangulum. The rest are mostly small dwarf galaxies, many of which orbit the Milky Way or Andromeda the way moons orbit planets. The Local Group spans about 10 million light-years across. In miles, that works out to roughly 59 quadrillion miles. If you could somehow travel at light speed, crossing from one side to the other would take 10 million years. But the Local Group is tiny compared to larger structures. It belongs to a larger collection called the Virgo supercluster. The Virgo supercluster contains about 100 galaxy groups and clusters, including our Local Group. At its heart sits the Virgo cluster, a dense concentration of more than 1,000 galaxies located about 54 million light-years from us. The Virgo supercluster spans roughly 110 million light-years in diameter. That is about 11 times the size of the Local Group. It contains perhaps 100 trillion stars in total. But even the Virgo supercluster is not the largest structure we belong to. In 2014, astronomers announced the discovery of an even larger structure called Laniakea. Laniakea is a supercluster complex containing about 100,000 galaxies. It stretches roughly 520 million light-years across, about 5 times the size of the Virgo supercluster. The Milky Way sits near the outer edge of Laniakea, in a relatively sparse region, and Laniakea is just one of many supercluster complexes that compose the cosmic web. Now, Let us discuss the web itself. The filaments of the cosmic web are where most galaxies in the universe reside. These filaments function like cosmic highways, rivers of dark matter and gas along which galaxies flow. A single filament can extend for hundreds of millions of light years. The filaments connect at nodes, which represent the densest regions of the universe. These nodes typically contain galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies, surrounded by vast halos of dark matter and superheated gas. Some of the largest clusters are truly enormous. The Coma cluster, located about 330 million light-years away, contains more than 1,000 galaxies. The galaxy cluster Abell 2029 is even larger, dominated by an enormous elliptical galaxy containing over 100 trillion stars. And then there are the voids. Voids are the empty spaces between the filaments. They are not completely empty. Some galaxies exist in voids, called void galaxies, but they are rare. The density of matter in a void can drop to as low as 10% of the average density of the universe. Some voids are staggeringly large. The Boots void, discovered in 1981, stretches roughly 330 million light-years in diameter. It contains fewer than 60 galaxies. For comparison, a region of that size in a typical part of the universe would contain about 10,000 galaxies. Even larger is the Giant Void, which spans about 1.3 billion light-years across. Picture a sphere of nearly empty space, 1 billion light-years wide, with almost nothing in it. The cosmic web is thought to have formed through the influence of dark matter. In the early universe, just after the Big Bang, matter was distributed almost uniformly, but not quite. There were tiny variations, regions slightly denser than average and regions slightly less dense. Over billions of years, gravity amplified these tiny differences. Matter flowed toward the denser regions and away from the less dense ones. Dark matter, which constitutes about 85% of all matter in the universe, formed the scaffolding. It collapsed first into filaments and nodes. Regular matter, the atoms that compose stars and planets and people, followed along, flowing into the gravitational wells that dark matter had already created. Galaxies formed along these dark matter filaments. They clustered at the nodes where multiple filaments met. And the voids, the regions where dark matter was scarce, emptied out as matter flowed away toward denser regions. What we observe today is the result of nearly 14 billion years of this process. The cosmic web is the skeleton of the universe, the framework on which everything else hangs. We have discussed how the estimate of galaxies jumped from 100 billion to approximately 2 trillion. But one of the most remarkable aspects of this is that most of those galaxies remain invisible to us. Even with our most powerful telescopes, we cannot detect them. Let us explore why. The galaxies we cannot see fall into several categories. Some are too distant, so far away that their light has not had time to reach us yet. Some are too faint, emitting so little light that they do not register on even our most sensitive instruments. And some are too small, physically compact in ways that make them extremely difficult to detect. But the biggest category is dwarf galaxies. These small, dim galaxies constitute the vast majority of all galaxies in the universe, and most of them remain invisible. Every telescope has a sensitivity limit, a threshold below which objects are too faint to detect. This limit depends on the telescope's size, its exposure time, the sensitivity of its detectors, and the background noise in the image. For galaxies, this sensitivity limit creates a strong bias toward bright, large galaxies. A galaxy, like the Milky Way, with hundreds of billions of stars, is easy to spot from billions of light years away. But a dwarf galaxy with only 1 million stars might be invisible at the same distance. The result is that our galaxy catalogues are heavily skewed toward large, bright galaxies. We see the Milky Ways and Andromedas of the universe. We miss the tiny dwarfs with only 1,000 stars. Astronomers use a measure called surface brightness to describe how much light a galaxy spreads across the area it covers on the sky. Surface brightness is measured in magnitudes per square arc second, describing how bright each tiny piece of the galaxy appears. Most galaxies we have detected have relatively high surface brightness. Their stars are concentrated enough that they stand out against the background glow of the sky. But there exists a whole population of galaxies, called low-surface brightness galaxies, that spread their light so thinly across space that they are nearly invisible. Ultra-diffuse galaxies represent an extreme example. These galaxies can span distances comparable to the Milky Way in diameter, but they contain so few stars that they have the surface brightness of a dwarf galaxy. They are like cosmic ghosts, physically enormous but almost impossible to detect. The first ultra-diffuse galaxies were discovered in the Virgo cluster in 1984. But they were mostly ignored for decades because they proved so difficult to study. It was only in 2015 that astronomers started finding them in large numbers using new survey techniques and very long exposure times. We now understand that ultra-diffuse galaxies are common. In the Coma cluster alone, astronomers have found over 800 of them. They may represent one of the most abundant types of galaxies in the universe, but because they are so faint, we have only recently started to find them. Another category of hidden galaxies consists of high redshift galaxies, galaxies so distant that their light has been stretched by the expansion of the universe into wavelengths our eyes and most telescopes cannot easily detect. When light travels through the expanding universe, it gets stretched. The wavelength grows longer. For visible light, this means the light shifts toward the red end of the spectrum. This phenomenon is called redshift, and it is how astronomers measure the distance to far-off galaxies. For very distant galaxies, the redshift becomes so extreme that light, which was originally visible, has been stretched into the infrared. Our eyes cannot perceive infrared light, neither can most optical telescopes. To observe these distant galaxies, you need infrared telescopes. This is one of the primary reasons the James Webb Space Telescope was built. Webb is optimized for infrared light, enabling it to see galaxies that remain invisible to telescopes like Hubble. And what Webb has found is remarkable. In its very first deep-field images, Webb revealed galaxies at redshifts that had never been observed before. Some of these galaxies emitted their light when the universe was only a few 100 million years old, less than 3% of its current age. These galaxies had been completely invisible before Webb turned its golden mirrors toward the sky. Many of these newly discovered galaxies are surprisingly bright and surprisingly massive. They formed earlier than our models predicted. This has forced astronomers to revisit their theories of galaxy formation. But the most important point for our purposes is this. Before Webb, these galaxies did not exist in our counts. They were part of the hidden population, galaxies we knew must be out there but could not see. Now, gradually, we are adding them to the census. There is also the problem of dust. Galaxies that are actively forming stars often contain substantial amounts of dust, tiny particles of carbon and silicon and other elements created in previous generations of stars. This dust absorbs visible light and re-emits it as infrared radiation. A dusty star-forming galaxy might be producing as much light as 100 billion suns, but most of that light gets absorbed by dust and converted to infrared. Invisible light? Such a galaxy might appear dim or even invisible. In infrared, it blazes like a beacon. These dusty galaxies were a major discovery of infrared astronomy. Before we had infrared telescopes capable of detecting them, we were systematically undercounting the amount of star formation happening across the universe. And finally, there are galaxies hidden behind other galaxies. When you look at the sky, you are looking through the disk of the Milky Way. In some directions, particularly toward the center of our galaxy, there are so many stars and so much dust that it becomes almost impossible to see anything beyond. This region is called the zone of avoidance, because astronomers must avoid it when surveying distant galaxies. But there are galaxies behind the zone of avoidance. We simply cannot see most of them. Recent surveys using infrared and radio telescopes have started to pierce this veil and discover the hidden galaxies behind it. In 2016, astronomers using radio telescopes announced the discovery of hundreds of previously unknown galaxies behind the Milky Way. Some were giant galaxies that had been completely hidden from view by the dust and stars of our own galaxy. All of these factors, the faintness of dwarf galaxies, the extreme redshift of distant galaxies, the obscuring effects of dust, the blocking of the zone of avoidance, they all contribute to the hidden population. When Consolis and his team estimated approximately 2 trillion galaxies, they were attempting to account for all these hidden populations. They used mathematical models based on how galaxies form and evolve to estimate how many faint, small galaxies must exist that we cannot directly detect. Their models suggest that about 90% of all galaxies in the observable universe are too faint to see with current technology. That means for every galaxy we can see, there are roughly 9 more that we cannot. Let us take time to appreciate the remarkable machines that make galaxy counting possible. These telescopes and instruments rank among the most sophisticated devices ever built by humans, and understanding them helps explain why our estimates keep changing. The Hubble Space Telescope was launched in 1990 aboard the Space Shuttle Discovery. It orbits Earth at an altitude of about 340 miles, above the atmosphere that blurs and distorts light for ground-based telescopes. Hubble's primary mirror measures about 94 inches across, which is not particularly large by modern standards, but its position above the atmosphere gives it extraordinary clarity. Hubble has been instrumental in counting galaxies. The famous deep field images we discussed earlier were only possible because Hubble could stare at small patches of sky for days at a time, collecting photons too sparse for any single moment of observation to reveal. Each photon landing on Hubble's detectors adds to the image, building up a picture of objects so faint that they remain invisible in shorter exposures. Over its more than 30 years of operation, Hubble has observed millions of galaxies. It has revolutionized our understanding of cosmic history, showing us what galaxies looked like when the universe was young and tracing how they have evolved over billions of years. But Hubble has limitations. It primarily observes invisible and near ultraviolet light. For the most distant galaxies, whose light has been stretched by the expansion of the universe into the infrared, Hubble can only see the very brightest examples. Fainter high redshift galaxies escape its notice entirely. This is where the James Webb Space Telescope enters the picture. Webb was launched in December of 2021 and began science operations in 2022. It is named after James Webb, who led NASA during the Apollo program. Webb is designed specifically for infrared observations. Its primary mirror measures about 256 inches across, nearly 3 times the diameter of Hubble's mirror. This larger size means Webb can collect more light, seeing fainter objects. And its infrared capabilities allow it to detect galaxies that are invisible to Hubble. Webb orbits the Sun at a point called the second Lagrange point, about 1 million miles from Earth. At this location, Webb always keeps Earth between itself and the Sun, which helps keep its instruments cold. Infrared detectors need to be very cold to work properly, because warm objects, including the telescope itself, emit infrared radiation. Webb operates at temperatures around -400 degrees Fahrenheit. The early results from Webb have been remarkable. In its first deep field images, Webb revealed galaxies at higher redshifts than any previously observed. Some of these galaxies emitted their light when the universe was less than 400 million years old, just 3% of its current age. These rank among the first galaxies that ever formed, and Webb can see them. Perhaps more surprisingly, some of these early galaxies are brighter and more massive than our theories predicted. According to our models of galaxy formation, there should not have been enough time in the young universe for such large galaxies to form. Finding them has forced astronomers to revisit their theories and consider whether galaxies grew faster in the early universe than previously thought. Webb is still in its early years of operation. Over the coming decades, it will observe thousands more distant galaxies, pushing our census deeper into cosmic history. Ground-based telescopes also play a crucial role in galaxy counting. While they cannot match the clarity of space telescopes, they can be much larger, and larger mirrors mean more light-collecting power. The Keck Observatory in Hawaii operates 2 telescopes with primary mirrors about 400 inches across each. The Very Large Telescope in Chile consists of 4 telescopes, with mirrors about 320 inches across, which can be used together to create an effective mirror of enormous size. These ground-based observatories use a technique called adaptive optics to partially compensate for atmospheric distortion. Lasers create artificial guide stars in the upper atmosphere, and computer-controlled mirrors adjust hundreds of times per second to cancel out the blurring effects of turbulent air. The result is images that approach the clarity of space-based telescopes. Ground-based telescopes are particularly important for spectroscopy, the analysis of light broken into its component wavelengths. Spectroscopy tells us what distant galaxies are composed of, how fast they are moving, and how far away they are. While Hubble and Webb can image galaxies efficiently, ground-based telescopes are often superior at obtaining detailed spectra. Looking to the future, even more powerful telescopes are on the horizon. The European Extremely Large Telescope is currently under construction on Cerro Armazones, a mountain in the Atacama Desert of Chile. When completed around 2028, it will have a primary mirror about 128 feet across, making it the largest optical telescope ever built. The ELT will be able to see fainter objects than any existing telescope, potentially revealing galaxies that are currently invisible. The Giant Magellan Telescope, also under construction in Chile, will combine 7 large mirrors to create an effective aperture of about 80 feet. The 30-meter telescope, planned for construction in Hawaii, will have a mirror about 100 feet across. In space, NASA's Nancy Grace Roman Space Telescope is scheduled to launch around 2026 or 2027. Roman will have the same size mirror as Hubble, but with a field of view 100 times larger. This enables it to survey large areas of sky quickly, discovering millions of galaxies in the process. Each of these new instruments will add to our galaxy census. Each one will push deeper into the infrared, see fainter objects, and cover more sky. The history of galaxy counting has been driven by technology. Each new telescope has revealed more galaxies than expected. There is every reason to expect this trend will continue. We have discussed galaxies as statistical objects, things to be counted and categorized. But each galaxy is unique, with its own history, its own structure, its own characteristics. Let us spend some time appreciating this individuality. Consider the Milky Way, our home. It is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars from which spiral arms extend. The bar stretches about 27,000 light-years long. The spiral arms wrap around this bar, trailing behind as the galaxy rotates. The Milky Way has 4 major spiral arms and several minor ones. Our Sun is located in a minor arm called the Orion Arm, sometimes called the Orion Spur. We sit about 26,000 light-years from the galactic center, roughly halfway out in the disk. At the center of the Milky Way sits a supermassive black hole called Sagittarius A star. This black hole has a mass about 4 million times that of the Sun. Despite its enormous mass, it is relatively quiet compared to the supermassive black holes in some other galaxies, which are actively consuming gas and shining brilliantly as what we call quasars, or active galactic nuclei. The Milky Way also has a halo of old stars and globular clusters surrounding the disk, as well as an enormous halo of dark matter extending far beyond the visible galaxy. Now consider Andromeda, our nearest large galactic neighbor. Andromeda is also a spiral galaxy, but it is larger than the Milky Way. It contains roughly 1 trillion stars, compared to our few 100 billion. Its disk spans about 220,000 light-years across, more than twice the diameter of the Milky Way. Andromeda has a more prominent central bulge than the Milky Way, giving it a slightly different appearance. It also has at least 2 distinct spiral arm segments that are visible in images, though its overall spiral structure is somewhat disturbed. Andromeda has its own supermassive black hole at its center, estimated at about 100 million solar masses, significantly larger than Sagittarius A star. And like the Milky Way, Andromeda has a retinue of satellite dwarf galaxies orbiting it. When Andromeda and the Milky Way eventually merge, assuming they do collide as many models predict, the combined galaxy will become something entirely new. The spiral structures will be destroyed by the gravitational chaos of the merger, and what remains will likely be an elliptical galaxy. Speaking of elliptical galaxies, let us consider M87, one of the most famous. M87 is a supergiant elliptical galaxy at the heart of the Virgo cluster, about 54 million light-years from Earth. It is enormous, containing several trillion stars, far more than the Milky Way or Andromeda. M87's most famous feature is its supermassive black hole, which was the first black hole ever to be directly imaged. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's black hole against a ring of superheated gas. This black hole has a mass about 6.5 billion times that of the Sun, more than 1,000 times larger than Sagittarius A star. M87 also has a powerful jet of material shooting out from near its black hole, extending for thousands of light-years. This jet is produced by gas falling toward the black hole and being accelerated to near-light speed by magnetic fields. The jet makes M87 one of the most powerful radio sources in the sky. Now consider something very different, an irregular galaxy like the Large Magellanic Cloud. The LMC is a satellite galaxy of the Milky Way, visible from the southern hemisphere as a hazy patch of light in the constellation Dorado. It sits about 160,000 light-years from Earth. The Large Magellanic Cloud has no regular structure. It is neither spiral nor elliptical, but has a chaotic, asymmetric shape. This is probably because gravitational interactions with the Milky Way have disturbed its structure over billions of years. Despite its irregular shape, the LMC is a hotbed of star formation. It contains the Tarantula Nebula, one of the most active star-forming regions in the local group. The Tarantula Nebula alone contains enough gas to form millions of new stars. The LMC also gave us one of the most important astronomical events of the 20th century. In 1987, a star in the LMC exploded as a supernova designated SN 1987A. This was the closest supernova observed since the invention of the telescope, and it provided invaluable data about how massive stars die. Each galaxy has stories like this. Each one has its own structure, its own black hole, its own history of star formation and mergers and evolution. When we say there are approximately 2 trillion galaxies, we are saying there are 2 trillion unique cosmic systems, each one different from all the others. The number of galaxies in the universe is not constant. It changes over time, and mostly it decreases. Galaxies merge. When 2 galaxies pass close to each other, gravity draws them together. They may orbit each other for millions of years, getting closer with each pass, until finally they combine into a single, larger galaxy. This process was much more common in the early universe, when galaxies were closer together. The young universe was a chaotic place of frequent collisions and mergers. Many of the large galaxies we see today are the products of multiple mergers, smaller galaxies that combined over billions of years. The Milky Way itself has consumed many smaller galaxies over its history. Even now, it is in the process of absorbing several dwarf galaxies. The Sagittarius Dwarf Spheroidal Galaxy, discovered in 1994, is being torn apart by the Milky Way's gravity. Streams of its stars wrap around our galaxy, and a much larger merger may be coming. The Milky Way and Andromeda are currently approaching each other at about 250,000 miles per hour. Earlier estimates suggested a collision was certain in about 4.5 billion years. More recent studies suggest the situation is more uncertain, with some models indicating the probability of a near-term direct merger may be only around 2%. And if a merger does occur, it might take closer to 7 or 8 billion years. The outcome remains an active area of research. If and when these galaxies merge, the galaxy count of the observable universe will decrease by 1. 2 galaxies will become 1. This is happening constantly throughout the universe. Galaxies merge, and the total count goes down. But new galaxies can also form. When large galaxies collide, the gravitational chaos can pull streams of gas and stars out into space. Sometimes, these streams condense into their own gravitationally bound structures, becoming new galaxies. These tidal dwarf galaxies increase the count. The balance, though, tilts toward fewer galaxies over time. Mergers outpace new formation. The early universe had many more galaxies than the present-day universe, even though those early galaxies were smaller on average. This is one of the insights that led to the revised estimate of approximately 2 trillion galaxies. When astronomers examined the early universe, they saw more galaxies per unit volume than in the local universe. Those extra galaxies did not disappear. They merged, combining into the larger galaxies we see today. By counting how many galaxies existed at different times in cosmic history and how that number changed, Consolis and his team could estimate how many small, faint galaxies must have existed that we cannot directly see. Looking to the future, the number of galaxies will continue to decline. Gravity will continue to pull galaxies together. Clusters will become denser and more massive, while the voids become emptier. Eventually, in the very far future, gravitationally bound structures will have consumed everything they can reach. Each galaxy cluster will have merged into a single giant elliptical galaxy, and those giant ellipticals will be separated from each other by distances so vast, expanded by dark energy, that they will never meet. The universe will become a collection of isolated island galaxies, each one alone in an expanding void with nothing else visible in any direction. That is trillions of years in the future. For now, we live in a universe of approximately 2 trillion galaxies, a busy cosmic neighborhood filled with structure and activity. We cannot discuss so many galaxies without addressing the inevitable question: is there life out there, in all those galaxies, on all those planets? Has anything else arisen that thinks and wonders and looks up at its sky? We simply do not know. This remains one of the greatest unanswered questions in science. But we can reason through the possibilities. The conditions for life, as we understand it, seem to require a few basic ingredients: a source of energy like a star, a solvent like liquid water, a supply of chemical elements, particularly carbon, nitrogen, oxygen, and others, and time, enough time for chemistry to become complex. In the Milky Way alone, there are likely more planets than stars. Observations from the Kepler Space Telescope and other planet-hunting missions suggest that most stars have at least one planet, and many have multiple planets. Some estimates suggest there could be 40 billion Earth-sized planets in habitable zones in our galaxy alone. The habitable zone is the region around a star, where temperatures might allow liquid water to exist on a planet's surface. Too close to the star and water boils away. Too far and it freezes solid. Now multiply that by approximately 2 trillion galaxies. If there are tens of billions of potentially habitable planets in the Milky Way, there might be billions of trillions of such planets across the observable universe. So where is everyone? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked this question over lunch with colleagues in 1950. If life is common and intelligence can evolve, then civilizations should have arisen long ago on many planets. Some of those civilizations should have developed technology. Some should have spread through their galaxies, perhaps through ours. We should see evidence of them, but we do not. There are many proposed solutions to the Fermi Paradox. Maybe we are alone. Perhaps life is easy to start, but intelligence is extraordinarily rare. Perhaps there is some filter, some barrier that prevents most life from becoming complex or intelligent or technological. Maybe civilizations are common but short-lived. Perhaps technological species inevitably destroy themselves through war or environmental collapse or some other catastrophe. Perhaps the universe is littered with the ruins of dead civilizations, but none have survived long enough to make themselves known across interstellar distances. Maybe they exist, but we cannot recognize them. Perhaps advanced civilizations use technologies so sophisticated that we cannot detect them. Perhaps they communicate in ways we do not know how to listen for. Maybe they have not visited us because the distances are simply too vast. Even at high speeds, crossing a galaxy takes thousands or millions of years. Perhaps civilizations simply cannot spread that far. limited by the same cosmic distances that limit us. Or maybe they know about us and are deliberately staying hidden. We do not know which explanation is correct. All of them are consistent with the evidence, which is to say, the absence of any evidence of other civilizations. What we do know is that so many galaxies provide an almost unlimited number of potential homes for life. If life exists anywhere else in the universe, it could be in any of those galaxies, on any of their countless planets. And yet, so far, we have found only silence. We have mentioned dark matter several times. It is time to explore this mysterious substance in more depth, because it plays a crucial role in the existence of galaxies themselves. Dark matter is called dark because it does not emit light. It does not interact with electromagnetic radiation at all, which means we cannot see it with any telescope, no matter how sensitive. And yet dark matter constitutes about 85% of all matter in the universe. We know dark matter exists because we can observe its gravitational effects. Galaxies rotate in ways that only make sense if they contain far more mass than we can see. Galaxy clusters bend light from more distant objects in ways that reveal hidden mass. The cosmic microwave background, the faint glow left over from the early universe, has patterns that require dark matter to explain. But we do not know what dark matter is made of. Despite decades of searching, no one has directly detected a dark matter particle. It remains invisible, detectable only through its gravity. Without dark matter, galaxies would not exist. In the early universe, just after the Big Bang, matter was distributed almost uniformly. There were tiny variations, regions slightly denser than average, and regions slightly less dense. But these variations were very small, perhaps 1 part in 100,000. Gravity tends to amplify density variations. Matter flows toward denser regions, making them denser still. But regular matter, the atoms that compose stars and planets, faced a problem. It was coupled to light. Photons and atoms bounced off each other constantly, and this created pressure that resisted gravitational collapse. Dark matter did not have this problem. It does not interact with light, so it could begin collapsing under its own gravity much earlier. Dark matter formed the first structures in the universe, the seeds around which everything else would later grow. By the time the universe was about 390,000 years old, it had cooled enough for atoms to form and light to travel freely. This released regular matter from its coupling to radiation, and when that happened, regular matter fell into the gravitational wells that dark matter had already created. Galaxies formed in the densest regions of dark matter. The dark matter provided the scaffolding, the gravitational framework, and regular matter flowed into it and collapsed to form stars. This is why the cosmic web looks the way it does. The filaments and nodes are traced by dark matter. The galaxies follow along, clustering where dark matter is densest, absent where dark matter is sparse. Every galaxy sits inside a halo of dark matter, an invisible sphere of mass that extends far beyond the visible stars and gas. The Milky Way's dark matter halo is thought to extend about 1 million light-years from the center of the galaxy, roughly 10 times the diameter of the visible disk. When we count approximately 2 trillion galaxies, we are really counting approximately 2 trillion dark matter halos that happen to contain enough regular matter to form stars. The visible galaxy is just the bright spot at the center of a much larger, invisible structure. Simulations suggest that there should be far more small dark matter halos than we observe small galaxies. This is called the missing satellites problem. The Milky Way should have thousands of small satellite dark matter halos, but we only see dozens of satellite dwarf galaxies. Where are the missing satellites? There are several possible explanations. Maybe the small halos exist but contain no stars, making them completely invisible. Maybe feedback from star formation blew the gas out of small halos before many stars could form. Maybe our understanding of dark matter is incomplete. This connects back to our galaxy count. If many dark matter halos contain no stars, then the number of dark matter structures in the universe is even larger than the number of galaxies. The count of approximately 2 trillion galaxies is just the tally of halos that manage to form enough stars to qualify as a galaxy. The total number of dark matter halos, visible and invisible, could be much higher. There is something almost poetic about the distances involved when we discuss galaxies. Not poetic in the sense of flowery language, but poetic in the sense that the numbers themselves contain a kind of beauty. Consider what it means for a galaxy to be 1 billion light-years away. The light from that galaxy left its stars when life on Earth was nothing more than simple, single-celled organisms. Multicellular life had not yet evolved. The oceans were full of bacteria and algae and nothing else. No fish, no plants on land, no animals of any kind. Just microbes, doing what microbes do for billions of years. That light traveled through space, across the void, for 1 billion years. During that journey, life on Earth went through the most dramatic transformations imaginable. Multicellular life appeared. Animals evolved. Fish colonized the oceans. Plants moved onto land. Dinosaurs rose and fell. Mammals inherited the Earth. Apes climbed down from trees. Humans emerged and built civilizations, and eventually built telescopes. And then, after all that time, after 1 billion years of travel, those photons landed on a detector and became a data point in our galaxy census. Every distant galaxy you see in an astronomy image is a time capsule. It shows you not what that galaxy looks like now, but what it looked like when its light began its journey toward us. We see the distant universe as it was, not as it is. This means that when we count galaxies at different distances, we are also counting them at different times. A survey of distant galaxies is also a survey of the history of the universe. We can watch galaxies form, evolve, merge, and change by looking at different distances which correspond to different ages. The universe is not just a place. It is also a history book, written in light, stretching back to the earliest moments when the first stars and galaxies came into being. When you look at a photograph of a galaxy cluster, you are not seeing a snapshot of a single moment. You are seeing multiple moments in time layered on top of each other. The nearest galaxies in the image show you recent light. The most distant ones show you ancient light. You are seeing the past piled up in front of you, layer after layer, stretching back billions of years. And somewhere out there, right now, light is leaving distant galaxies that will not arrive at Earth for billions of years. Future astronomers, if any exist, will see those galaxies as they are today. They will have their own time capsules, their own messages from the past. Let us try once more to grasp the scale of what we have been discussing. Approximately 2 trillion galaxies. If you could visit one galaxy every second, it would take you about 63,000 years to visit them all. That exceeds the span of modern humans on this planet. Civilization is only about 10,000 years old. You would not finish your tour. If every person on Earth were assigned an equal number of galaxies, each person would receive about 250 galaxies. 250 entire galaxies, each with billions of stars for every man, woman, and child alive today. The number is simply too large for human intuition. We evolved in small groups, where the biggest numbers we needed to handle were the dozens of people in our tribe or the hundreds of animals in a herd. Our brains did not evolve to process trillions. And yet, through mathematics and science, we can work with these numbers. We can calculate with them, reason about them, use them to build models of the universe. Our intuition fails, but our tools succeed. This represents one of the great triumphs of the human mind. We have extended our reach far beyond our evolved capabilities. We have built instruments that see what our eyes cannot, measured distances that our feet could never walk, counted objects that our fingers could never enumerate. We cannot truly grasp what these numbers mean, but we can know that they are true. We can understand them intellectually, even if we cannot feel them emotionally. And that knowing, that understanding, is a kind of achievement. Our understanding of the universe is not complete. It will never be complete. Every generation of astronomers pushes the frontier a little further, sees a little deeper, understands a little more. Right now, as you listen to this, there are telescopes around the world collecting light from distant galaxies. The James Webb Space Telescope floats at a point about 1 million miles from Earth, its golden mirrors gathering infrared light from the edge of the observable universe. Ground-based observatories in Chile and Hawaii and the Canary Islands are imaging faint objects that have never been seen before. Computers are processing the data, looking for patterns, identifying new galaxies. Astronomers are analyzing the results, revising their models, updating their estimates. The figure of approximately 2 trillion is our current best estimate. It will almost certainly change. As we build better telescopes and develop new techniques, we will find more hidden galaxies. The estimate may go up. It probably will go up. In a decade, we might say 3 trillion galaxies. In a century, who knows? This is the nature of science. We never have final answers, only our best understanding at the moment. And our best understanding keeps getting better. The universe does not reveal itself all at once. It gives up its secrets slowly, one observation at a time. We have been studying the sky for thousands of years, and we are still just beginning to understand what is out there. Consider how much our view has changed in just the past century. In 1920, most astronomers believed the Milky Way was the entire universe. The fuzzy patches of light called nebulae were thought to be clouds of gas within our galaxy. By 1930, Edwin Hubble had proven that many of those nebulae were actually separate galaxies, far outside the Milky Way. The universe had suddenly become much larger. By 1960, astronomers had mapped thousands of galaxies and discovered that they were distributed in clusters and superclusters. By 1995, the Hubble Deep Field revealed galaxies at distances that had never been seen before, pushing our view back to when the universe was young. By 2016, the estimate of galaxies had jumped from around 100 billion to approximately 2 trillion. By 2023, Webb was finding galaxies even more distant and ancient than Hubble had seen. The story is one of constant expansion, of the universe getting bigger and more complex with every advance in our technology. There is no reason to think this expansion of knowledge will stop. Future telescopes will see even fainter objects. Future surveys will cover even more of the sky. Future theories will make sense of what we find. And in a century or two, people may look back at our estimate of approximately 2 trillion galaxies the way we look back at earlier estimates. They may smile at how much we did not yet know. That is okay. That is how science works. Each generation does the best it can with the tools available, and each generation leaves more questions than answers for those who come after. The search continues. What does all of this mean for us as human beings? We started with a question. How many galaxies are there in the observable universe? The answer, as best we can determine, is approximately 2 trillion. But that number is just the beginning of a much deeper story. That number tells us about the scale of the cosmos, about how small we are relative to everything that exists. But it also tells us about human ingenuity, about our ability to build instruments that can detect light from across the universe and piece together a picture of something so vast that no single mind can fully comprehend it. We are limited creatures. Our lives last less than a century. Our eyes can only see a narrow band of electromagnetic radiation. Our brains evolved to track a few dozen other humans and some prey animals, not to comprehend trillions of galaxies spread across billions of light years. And yet, we do comprehend it, in a way. We have developed mathematics and physics and engineering that allow us to extend our senses far beyond their natural limits. We have built telescopes that can see infrared light that our eyes cannot detect. We have developed cameras that can collect photons for days at a time, building up images of objects too faint to see in any single moment. We have created computers that can analyze billions of data points and reveal patterns no human could find on their own. Through these tools, we have learned that we live in a universe of staggering size and complexity. We have learned that our galaxy is one of approximately 2 trillion, that the observable universe is 93 billion light-years across, that most of what exists remains invisible to us. This knowledge is humbling. It puts all of human history in perspective. Our wars and triumphs, our art and science, our loves and losses, all of it has happened on one small planet, orbiting one ordinary star in one average galaxy. The universe does not know we exist. And yet, there is something defiant about the fact that we know this. The universe may not know about us, but we know about it. We are the part of the universe that asks questions, that seeks answers, that builds telescopes and maps the cosmos. Every galaxy in the sky is an island universe, a vast collection of matter and energy that will never interact with us in any meaningful way. The distances are too great, the speed of light is too slow. We are separated from nearly everything that exists by gulfs of space and time that can never be crossed. And yet we see them. We know they are there. We can count them, study them, wonder about them. Consider what the light we see from distant galaxies represents. When we look at a galaxy a billion light-years away, we are seeing it as it was a billion years ago. The light we collect tonight left that galaxy when life on Earth was nothing but single-celled organisms. What is that galaxy like now, today, in this moment? We have no way of knowing. The light from that galaxy showing its current state will not reach Earth for another billion years. We live in a universe where even light, the fastest thing there is too slow to connect distant places in real time. We are isolated in the present, able only to see the past. And yet, despite this isolation, there is a profound connection. The atoms in your body were made in stars, and those stars were in galaxies. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was forged in the hearts of stars that exploded long ago, scattering their elements across space. You were made of star stuff, and those stars were in galaxies, and those galaxies were part of the cosmic web. You are connected to all of it through the matter that makes you up. Our understanding that galaxies exist beyond the Milky Way is surprisingly recent. For most of human history, people had no idea that the fuzzy patches of light visible in the night sky were anything other than clouds of gas within our own galaxy. The story begins in the 18th century. In 1755, the philosopher Immanuel Kant proposed what he called island universes. He suggested that some of the nebulae, the fuzzy patches visible through telescopes, might be distant systems of stars similar to the Milky Way. It was a brilliant intuition, but he had no way to prove it. Throughout the 19th century, astronomers catalogued thousands of nebulae. Charles Messier compiled his famous catalogue of fuzzy objects, originally intended to help comet hunters avoid confusion. William Herschel and his son John mapped even more. But the fundamental question remained unanswered. Were these nebulae clouds of gas within the Milky Way, or were they distant galaxies in their own right? The debate came to a head in 1920, in what became known as the Great Debate. Harlow Shapley argued that the Milky Way was essentially the entire universe, and that the spiral nebulae were relatively nearby gas clouds. Heber Curtis argued that the spiral nebulae were island universes, separate galaxies far beyond our own. The debate was settled in 1923, when Edwin Hubble observed Cepheid variable stars in the Andromeda Nebula using the 100-inch Hooker telescope at Mount Wilson Observatory. Cepheid variables are stars that pulsate in a regular pattern, and their pulsation period is directly related to their intrinsic brightness. By measuring how bright a Cepheid appears versus how bright it actually is, you can calculate its distance. Hubble's Cepheid measurements showed that Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy entirely, roughly 900,000 light-years away. We now know the actual distance is about 2.5 million light-years. But even Hubble's underestimate was enough to prove the point. The universe suddenly became vastly larger than anyone had imagined. In the years that followed, Hubble and others identified galaxies across the sky. They developed classification systems based on shape. They measured distances to more and more galaxies. And in 1929, Hubble made another discovery that would reshape cosmology. He found that distant galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding. This discovery was the first observational evidence for what we now call the Big Bang. If galaxies are moving apart today, then in the past they must have been closer together. Run the clock back far enough, and all the matter in the universe was compressed into an incredibly hot, dense state. The expansion we observe today is the continuation of the expansion that began at the very beginning of time. From Hubble's initial identification of a few dozen galaxies, the count has grown steadily. By the 1950s, astronomers had catalogued thousands. By the 1970s, the count was in the hundreds of thousands. The Sloan Digital Sky Survey, begun in 2000, has mapped the positions of millions of galaxies, and our best estimates now suggest approximately 2 trillion exist within the observable universe. This progression from thinking nebulae were local gas clouds to estimating 2 trillion galaxies happened in less than a century. It represents one of the most dramatic expansions of human knowledge in history. When we look at galaxies, the view depends entirely on what kind of light we use. Visible light, the kind our eyes can see, tells only part of the story. Other wavelengths reveal completely different aspects of galactic structure and activity. Radio waves, the longest wavelength form of electromagnetic radiation, penetrate dust and gas that block visible light. Radio telescopes can see through the Milky Way's disk to observe galaxies on the other side. They can detect the cold hydrogen gas that fills the space between stars, mapping reservoirs of raw material for future star formation. And they can observe jets of material shooting out from supermassive black holes accelerated to nearly the speed of light. The Event Horizon Telescope, which produced the first image of a black hole's shadow in galaxy M87, operates at radio wavelengths. By combining signals from radio dishes around the world, it achieves the angular resolution equivalent to a telescope the size of Earth. Infrared light reveals the warm dust that pervades star-forming regions. Young stars are often hidden behind cocoons of dust that absorb their visible light and re-emit it as infrared. Infrared telescopes can peer through these dusty shrouds to observe stars in the process of being born. Infrared is also crucial for observing distant galaxies. Because the universe is expanding, light from faraway galaxies gets stretched to longer wavelengths during its journey. Light that started as visible shifts into the infrared by the time it reaches us. This is why the James Webb Space Telescope, optimized for infrared, can see galaxies that are invisible to optical telescopes like Hubble. Ultraviolet light comes from the hottest, youngest stars. Because massive stars burn through their fuel quickly, they do not last long in cosmic terms. A galaxy rich in ultraviolet light is actively forming new stars. A galaxy lacking ultraviolet emission has used up its gas and stopped producing young stars. X-rays reveal the most violent processes in the universe. They come from gas heated to millions of degrees, from the accretion disks around black holes, from the remnants of exploded stars. The hot gas that fills galaxy clusters, called the intracluster medium, glows brightly in X-rays. Mapping this X-ray emission tells us about the distribution of mass in clusters and helps us trace the cosmic web. Gamma rays are the highest energy form of light. They come from the most extreme events imaginable: supernova explosions, gamma ray bursts, jets from active galactic nuclei. Gamma ray observations have revealed populations of galaxies that are virtually invisible at other wavelengths. Their activity hidden except in these most energetic photons. By observing galaxies across the entire electromagnetic spectrum, from radio to gamma rays, astronomers build a complete picture. Each wavelength adds information that the others cannot provide. A galaxy might look quiet and boring in visible light, but blaze with activity in X-rays, revealing a hidden supermassive black hole consuming material. Another might appear ordinary in visible light, but glow with star formation visible only in infrared. Our census of approximately 2 trillion galaxies is built from observations across all these wavelengths. Missing any one would leave our picture incomplete, and entire populations of galaxies would be missed. Among the billions of galaxies we have catalogued, some stand out as particularly interesting, extreme, or scientifically important. Let us highlight a few that deserve special mention. The Whirlpool Galaxy, also known as M51, is one of the most beautiful spiral galaxies visible from Earth. It lies about 23 million light-years away and is interacting with a smaller companion galaxy called NGC 5195. This interaction has triggered extensive star formation and has pulled one of M51's spiral arms out toward the companion. The Whirlpool was the first galaxy in which spiral structure was recognized back in 1845 by Lord Rosse using his massive telescope in Ireland. The Sombrero Galaxy, or M104, appears as a bright nucleus surrounded by a large dust lane, giving it the appearance of a Mexican hat when viewed edge-on. It lies about 30 million light-years away and contains an exceptionally massive central black hole estimated at 1 billion solar masses. Despite its relatively close distance, the sombrero has puzzled astronomers because its star population suggests it is older than most nearby spiral galaxies. The Cigar Galaxy, M82, is a starburst galaxy about 12 million light-years away. It is undergoing intense star formation, triggered by a gravitational interaction with its larger neighbor M81. Stars are forming in M82 at a rate about 10 times higher than in typical galaxies. This activity is visible as jets of hydrogen gas streaming out from the galaxy's core, extending thousands of light-years into intergalactic space. Centaurus A is one of the nearest radio galaxies at about 13 million light-years. It appears as an elliptical galaxy bisected by a dramatic dark dust lane. This peculiar appearance suggests that Centaurus A resulted from a merger between an elliptical galaxy and a spiral galaxy, with the dust lane being the remnant of the spiral's disk. A powerful jet shoots out from the galaxy's central black hole, extending over 1 million light-years into space. The Cartwheel Galaxy, about 500 million light-years away, shows what happens when a galaxy collision goes just right. A smaller galaxy passed directly through the center of a larger spiral, sending a ripple of star formation expanding outward like the rings from a stone dropped in a pond. The result is a spectacular ring-shaped galaxy with intense starburst activity around its circumference. Hoag's object is one of the strangest galaxies known. It consists of a nearly perfect ring of blue stars surrounding a core of yellow stars, with almost nothing visible in between. Discovered in 1950 by Arthur Hoag, it remains unexplained. One theory suggests it formed from a collision, but no second galaxy is visible. Another suggests it might be an extreme example of a barred spiral seen face-on, but this fails to explain the empty gap. Hoag's object remains a mystery. The Tadpole Galaxy, about 420 million light-years away, displays an enormously long tail of stars stretching over 300,000 light-years. This tail was pulled out during a close encounter with a smaller galaxy, visible in images near the tadpole's head. The tail contains numerous bright blue star clusters, newly formed from gas compressed by the interaction. ARP-87 is a pair of interacting galaxies about 300 million light-years away. The two galaxies are connected by a bridge of stars, gas, and dust drawn out by their mutual gravitational attraction. This is a snapshot of a galaxy merger in progress, showing what happens when two galactic systems begin to combine. Each of these galaxies tells us something different about galactic physics, about how galaxies form, evolve, collide, and change over time. Our catalogue of approximately 2 trillion galaxies includes countless similar examples, each one a unique laboratory for studying the universe. Some galaxies push the boundaries of what we thought possible. They are the biggest, the smallest, the oldest, the brightest, or the most distant. These extreme examples help define the range of what a galaxy can be. The question of which galaxy is the largest is surprisingly complicated because galaxies do not have sharp edges. Their halos fade gradually into intergalactic space. But, by most measures, Alcyonius currently holds the record. Discovered in 2022, Alcyonius is a radio galaxy whose jets extend about 16 million light-years from end to end. This makes it the largest known structure associated with a single galaxy. The galaxy itself is not especially large, but its jets dwarf everything else. On the opposite end, the smallest galaxies are almost not galaxies at all. Segue 2, which we mentioned earlier, contains only about 1,000 stars within a region about 115 light-years across. Its total mass is dominated by dark matter. Galaxies this small blur the boundary between a galaxy and a star cluster, and astronomers debate whether some of these objects should be classified as galaxies at all. The most distant galaxy currently known has the uninspiring name JADES GSZ140, identified by the James Webb Space Telescope in 2024. Its light comes from a time when the universe was only about 290 million years old, less than 2% of its current age. This galaxy existed when the universe was just emerging from its dark ages, when the first stars were igniting and the first galaxies were assembling from smaller building blocks. The most luminous galaxies are quasars, objects where a supermassive black hole is actively consuming material at a tremendous rate. The accretion disk around such a black hole can outshine the entire galaxy of stars surrounding it. Some quasars emit more light than 10 trillion suns. They can be seen from across the observable universe, serving as beacons that illuminate the intergalactic medium between us and them. The oldest galaxies are presumably about as old as the universe itself, around 13.8 billion years. But identifying the oldest individual galaxy is challenging because we can only see galaxies as they appeared when their light left them. A galaxy seen at a distance of 13 billion light-years is seen as it was 13 billion years ago when it was young. The oldest galaxies today are probably large ellipticals in nearby galaxy clusters, which formed early and have been aging quietly ever since. The most massive galaxies contain several trillion stars each. IC 1101, which we mentioned earlier, is one of the largest. These giant ellipticals typically sit at the centers of galaxy clusters, having grown through repeated mergers over billions of years. They have consumed many smaller galaxies, absorbing their stars and adding to their bulk. The loneliest galaxies sit in the centers of cosmic voids, far from any neighbors. Some void galaxies are millions of light-years from the nearest significant structure. They evolve in isolation, undisturbed by the gravitational interactions that shape galaxies in denser environments. Studying these isolated systems helps astronomers understand how galaxies develop when left to themselves. These extremes help bracket our understanding. Between the smallest and largest, between the nearest and most distant, between the youngest and oldest, lie approximately 2 trillion galaxies of every intermediate variety. How did galaxies first form? This question has driven observational cosmology for decades, and we are finally beginning to see answers. The universe began with the Big Bang about 13.8 billion years ago. For the first few 100 million years, there were no galaxies. There were no stars. The universe was filled with hydrogen and helium gas, cooling and expanding, with subtle variations in density laid down during the first moments of existence. Gravity slowly amplified these density variations. Regions that started slightly denser attracted more matter from their surroundings. The denser they became, the stronger their gravitational pull, and the faster they accumulated additional material. This process, called gravitational collapse, eventually produced the first stars. These first stars were probably very different from stars today. They formed from pristine hydrogen and helium, without the heavier elements that later generations of stars would produce. Theoretical models suggest they were very massive, perhaps hundreds of times the mass of the Sun, and extremely luminous. They lived fast and died young, exploding as supernovae after only a few million years. These explosions scattered heavier elements into space, seeding future generations of stars and planets with the materials necessary for rocky worlds and life. The first galaxies assembled from collections of these early star-forming regions. They were small by modern standards, perhaps just a few million stars each. But gravity continued its work, drawing these proto-galaxies together into larger and larger structures. Mergers were common. Small galaxies combined to form medium-sized galaxies. Medium-sized galaxies combined to form large ones. This hierarchical assembly process continues today, though the most dramatic mergers happened early in cosmic history. Modern large galaxies, like the Milky Way, are the products of dozens or hundreds of past mergers. Their stars mix together like ingredients in a cosmic stew. The James Webb Space Telescope is revolutionizing our understanding of early galaxy formation. Its infrared sensitivity allows it to observe galaxies from the first billion years of cosmic history, an era that was largely invisible to previous telescopes. What Webb has found is surprising. Some of the early galaxies are larger and more massive than our models predicted. According to standard theory, there should not have been enough time for such substantial galaxies to form so quickly. Either galaxies assembled faster than we thought, or stars formed more efficiently in the early universe, or our models need revision. Some early galaxies also show signs of mature stellar populations, stars that appear older than expected given the young age of the universe at that time. This remains an active puzzle, with theorists working to reconcile observations with models. The very first galaxies, those that formed in the first few 100 million years, may forever remain beyond our direct observation. Even Webb cannot see far enough back to witness the moment of first light. But by studying increasingly distant and ancient galaxies, we can trace the story backward, inferring what must have come before. The space between galaxies is not truly empty. It contains the intergalactic medium, a thin soup of gas and dark matter that permeates the cosmic web. This gas is incredibly sparse. In the densest regions of the intergalactic medium, there might be a few atoms per cubic foot. That is a better vacuum than anything we can produce in a laboratory on Earth. In the voids between filaments, the density drops even lower. Yet this gas, spread across the vastness of intergalactic space, contains more matter than all the stars in all the galaxies combined. The intergalactic medium consists mostly of hydrogen and helium, the primordial elements created in the Big Bang. Some of this gas has never been incorporated into any galaxy. It has been drifting through space for nearly 14 billion years, unchanged since the first moments of the universe. Other regions of the intergalactic medium have been enriched with heavier elements. Supernova explosions in galaxies drive powerful winds that push gas, including the newly forged heavy elements, out into intergalactic space. This enriched gas mixes with the primordial material, slowly increasing the heavy element content of the universe as a whole. The temperature of the intergalactic medium varies dramatically. In the filaments of the cosmic web, shock waves from infalling matter have heated the gas to millions of degrees. This hot gas emits X-rays and can be detected by space-based X-ray telescopes. In the voids, the gas is cooler, perhaps only a few thousand degrees left over from the cooling after the Big Bang. Galaxy clusters contain particularly dense regions of intergalactic gas called the intracluster medium. This gas is so hot, heated by the gravitational compression of matter falling into the cluster, that it glows brightly in X-rays. In fact, the mass of the intracluster medium typically exceeds the total mass of all the stars in all the galaxies within the cluster. Most of the normal matter in clusters exists not in galaxies, but in this hot, diffuse gas between them. Light from distant quasars passes through the intergalactic medium on its way to us. The gas absorbs certain wavelengths of light, creating absorption lines in the quasar's spectrum. By studying these absorption lines, astronomers can map the distribution of gas along the line of sight, measuring the density and composition of the intergalactic medium at different distances and cosmic epochs. This technique has revealed that the intergalactic medium traces the cosmic web. Gas is concentrated along the filaments and nodes where gravity has drawn matter together. The voids, as expected, contain much less gas. The intergalactic medium is also where much of the missing normal matter in the universe hides. When astronomers add up all the stars, gas, and dust in galaxies, they find only about half the normal matter that Big Bang theory predicts should exist. The other half is in the intergalactic medium, too hot and diffuse to observe easily but detectable through careful observations at X-ray and ultraviolet wavelengths. Understanding the intergalactic medium is essential for understanding galaxies themselves. Galaxies do not exist in isolation. They are nodes in a vast web, fed by streams of gas flowing along filaments, shaped by the environment in which they reside. What will become of all these galaxies over the coming billions and trillions of years? The future of galactic evolution is written in the laws of physics, and it tells a story of gradual darkening and increasing isolation. In the near future, by cosmic standards, the local group will continue its slow gravitational dance. The Milky Way is currently consuming several dwarf satellite galaxies, adding their stars to its own. Andromeda is doing the same. Eventually, as we discussed, these two largest members of the local group may merge into a single giant elliptical galaxy. Over the next few billion years, the other members of the local group will also be absorbed. Triangulum, the third largest galaxy in our neighborhood, will likely merge with the combined Milky Way Andromeda system. The smaller dwarfs will be tidally disrupted and their stars dispersed. The end result, perhaps 10 to 20 billion years from now, will be a single enormous elliptical galaxy containing the combined stellar populations of everything currently in the local group. This future galaxy has been nicknamed Milkomeda or Milkdromeda by astronomers with a sense of humor. But what happens on larger scales is more ominous. The universe is expanding, and that expansion is accelerating due to dark energy. As space stretches, distant galaxies move farther away from us. The farther away they are, the faster they recede. Eventually, the expansion of space will carry other galaxy clusters beyond our cosmic horizon. The Virgo cluster, the Coma cluster, the great superclusters that define the cosmic web, all of them will slide beyond the point where their light can reach us. They will effectively disappear from our observable universe. This process takes a long time by human standards, but is inexorable. In about 100 billion years, nearly every galaxy beyond the local group will have receded past our cosmic horizon. Observers in the Milkomeda galaxy at that distant future time will look out at a mostly empty universe. They will see their own galaxy and perhaps a few gravitationally bound neighbors, but the rest of the cosmic web will be invisible, forever unreachable, as if it had never existed. If intelligent beings arise in that far future, they may conclude wrongly that the universe contains only a single galaxy, their own. The evidence of the Big Bang, the cosmic microwave background radiation, will have been stretched by expansion to wavelengths so long that it will be undetectable. The distant galaxies that today tell us the universe is expanding will be gone beyond all observation. Future astronomers may never know what we have the privilege of seeing today. On even longer timescales, the stars themselves will die. The Milky Way galaxy will exhaust its gas for forming new stars. The last stellar generations will burn through their fuel and fade. Red dwarfs, the longest-lived stars, can shine for trillions of years, but eventually even they will cool and dim. After perhaps 100 trillion years, the last stars will wink out. The galaxy will become a dark collection of stellar remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning down, black holes slowly evaporating through Hawking radiation. The beautiful spiral arms and glowing star clusters we see today will be long gone, remembered by no one. This is the fate that awaits all approximately 2 trillion galaxies in the observable universe. Each one will follow the same trajectory, from vibrant collections of stars to dark graveyards of stellar remnants. The cosmic web will stretch and fade into nothing. The universe will grow cold and dark and empty, but that is unimaginably far in the future. For now, and for billions of years to come, the universe remains a bright and dynamic place, full of galaxies being born and galaxies dying, stars igniting and stars exploding, the cosmic web glowing with activity. We live in a special time, early enough in cosmic history that the universe is still alive with light, that galaxies are still visible across billions of light years, that the evidence of our origins is still written across the sky. We should appreciate this era while we can. For all our technological achievements, there are aspects of galaxies that remain beyond observation. Some things about the universe we can only infer, not see directly. We cannot observe dark matter. We know it is there because of its gravitational effects, but it emits no light and reflects no light. We infer the dark matter halos surrounding galaxies from the way galaxies rotate, from the way light is bent around galaxy clusters, from the patterns in the cosmic microwave background. But we have never seen dark matter directly. We do not even know what it is made of. After decades of experiments searching for dark matter particles, none have been definitively detected. We cannot observe dark energy either. We know it exists because the expansion of the universe is accelerating, and something must be driving that acceleration. But we do not know what dark energy is. We cannot point a telescope at it. We can only measure its effects and try to infer its properties from how the universe evolves. We cannot observe the interior of black holes. The event horizon marks a boundary from which no light can escape. Whatever happens inside that boundary is forever hidden from outside observers. General relativity tells us that matter falling into a black hole eventually reaches a singularity, a point of theoretically infinite density. But singularities represent a breakdown of our physics. What actually happens at the center of a black hole remains unknown and may be unknowable. We cannot observe the universe before it became transparent. For the first 380,000 years after the Big Bang, the universe was so hot and dense that light could not travel freely. Photons scattered constantly off electrons in the plasma that filled space. Only when the universe cooled enough for atoms to form did light begin to travel in straight lines. The cosmic microwave background is light from that moment of first transparency. Anything that happened before is hidden behind a wall of scattered radiation that our telescopes cannot penetrate. We cannot observe what lies beyond our cosmic horizon. Light from those regions has not had time to reach us since the Big Bang. They may be out there, full of galaxies and stars, and perhaps even life, but we can never see them, never communicate with them, never know for certain that they exist. We cannot observe the future. We can predict what might happen based on physical laws, but we cannot see it directly. The fate of galaxies, the evolution of stars, the eventual cold darkness of the far future, all of these are inferences from theory, not observations. These limitations remind us that our view of the universe, impressive as it is, remains incomplete. The approximately 2 trillion galaxies we can count represent only a fraction of what exists. The visible matter in those galaxies represents only a fraction of their total mass. The light we can observe represents only a fraction of their history. We are like explorers with a tiny flashlight in a vast dark cavern. We can see what our light illuminates, but the darkness extends far beyond our beam. Every advance in technology pushes the boundary of our light a little further, revealing more of the cavern, but the darkness always recedes ahead of us. There is always more that we cannot see. This is not cause for despair, but for wonder. The universe is larger and more mysterious than we can ever fully grasp. Our approximately 2 trillion galaxy estimate is not the final word, but a milestone on a journey of discovery that will continue as long as humans look up at the stars. Before we close our eyes for the night, let us spend a moment appreciating something often overlooked: the colors of galaxies and what they tell us. Galaxies are not all the same color. Some glow blue-white, some appear golden-yellow, some are reddish. These colors carry information about the galaxies themselves, about their ages and activities and histories. Blue galaxies are typically full of young, hot stars. Massive stars burn through their nuclear fuel quickly and shine with intense blue light. They do not last long, perhaps only millions of years, before exploding as supernovae. So when you see a galaxy tinted blue, you know that new stars have formed recently. Star formation is actively happening. Gas is collapsing into dense clouds and igniting new stellar furnaces. Spiral galaxies often appear blue in their arms because that is where star formation concentrates. The spiral pattern is actually a density wave, a compression moving through the galaxy's disk. Gas passing through this wave gets compressed and collapses into new stars. The blue light of those young stars traces the spiral pattern. Red and yellow galaxies are dominated by older stars. Low-mass stars live for billions of years, slowly burning through their fuel. As they age, they cool and redden. A galaxy that stopped forming new stars long ago will appear red or golden, lit only by its elderly stellar population. Elliptical galaxies typically appear this way. They have used up their gas or had it stripped away by interactions with other galaxies, or the hot gas in galaxy clusters. Without fuel for new star formation, they are slowly fading, their stellar populations aging gracefully together. The color of a galaxy can also be affected by dust. Dust absorbs blue light more effectively than red light, so a dusty galaxy may appear redder than its stars would otherwise suggest. This is similar to why sunsets on Earth appear red. The short blue wavelengths get scattered and absorbed, while the longer red wavelengths pass through. Extremely distant galaxies appear red for a different reason: the stretching of their light by cosmic expansion. Light that started out blue has been shifted toward the red end of the spectrum during its long journey to us. This cosmological redshift affects all wavelengths, moving the entire spectrum toward longer wavelengths. The most distant galaxies we observe have been so extremely redshifted that their light has moved entirely out of the visible range and into the infrared. When astronomers create color images of galaxies, they are not just making pretty pictures. They are encoding scientific information. The distribution of colors across a galaxy reveals where stars are forming, where they are not, how dust is distributed, and how old different stellar populations might be. Some of the most striking galaxy images show the contrast between blue spiral arms and yellow central bulges. The arms are sites of active star birth. The bulges contain older stars that formed early in the galaxy's history. You are seeing the archaeological record of the galaxy's life, different chapters written in different colors. Look at any deep field image of distant galaxies, and you will see this diversity of color. Some galaxies glow blue, vigorously forming new generations of stars. Others have turned red, their star forming days behind them. Still others show complex patterns, blue regions and red regions mixed together, telltale signs of complicated histories involving mergers, interactions, and waves of star formation. Color is information. The universe is not painted in arbitrary shades. Every hue tells a story of physics and chemistry and time, if you know how to read it. Consider for a moment the improbable chain of events that led to you lying here, listening to words about galaxies. It begins with the Big Bang, 13.8 billion years ago. Hydrogen and helium formed in the first minutes. Dark matter began pulling ordinary matter into clumps. The first stars ignited, burning their fuel and exploding, seeding space with heavier elements. Galaxies assembled from these stellar remnants. Our Milky Way took shape, accumulating stars from countless mergers and encounters. One ordinary star, our Sun, formed about 4.5 billion years ago in an unremarkable arm of the galaxy. Around the Sun, planets coalesced from the disk of gas and dust. Earth settled into an orbit where liquid water could exist. Life emerged, perhaps in hydrothermal vents at the bottom of ancient oceans, single cells at first, then multicellular organisms, then the explosion of complex life. Species came and went. Dinosaurs dominated for over 160 million years before an asteroid ended their reign. Mammals, previously small and marginal, diversified into the empty niches. Primates evolved. Apes climbed down from trees. Hominids walked upright across the African savanna. Humans developed language, then writing, then mathematics. We began to observe the sky systematically. We invented telescopes and discovered that the fuzzy patches in the night sky were other galaxies. We launched instruments into space and built detectors sensitive enough to count photons from billions of light years away. And now you are here, a product of all that cosmic and biological history, listening to an account of how many galaxies exist. The atoms in your body were forged in stars that exploded before the sun was born. You are the universe contemplating itself. This is not mysticism. This is the straightforward conclusion of physics and biology. You are made of matter that has been part of multiple generations of stars. You exist on a planet orbiting one star among hundreds of billions in one galaxy, among approximately 2 trillion. The story of the universe and the story of you are not separate. They are the same story, told at different scales. When you look at images of distant galaxies, you are looking at your extended family, cosmically speaking. Those galaxies contain the same elements, formed by the same processes, governed by the same physical laws. If life exists elsewhere in the universe, it will be built from the same periodic table of elements, the same basic chemistry that underlies life on Earth. We are not strangers in this universe. We are natives, born from its substance, shaped by its laws, connected to everything else by the common thread of matter and energy and time. The night is quiet now. The questions about galaxies can wait. The numbers and distances and scales can rest until tomorrow. For now, there is just the darkness and your breathing and the slow settling of thoughts. Somewhere out there, light is still streaming toward us from distant galaxies. Photons that left their source billions of years ago are arriving at Earth right now, their journey almost complete. Tomorrow, or next year, or next century, they will land on the mirror of a telescope and be recorded, adding one more data point to our understanding of the universe. But that is for later. That is for waking hours. For now, let the scale of the universe be comforting rather than overwhelming. Let the vastness be a kind of peace. All those galaxies, all those stars and planets and maybe even life, all of it out there spinning through the void, and here you are, safe and warm, drifting towards sleep. The universe will still be there in the morning. The galaxies will still be in their places. The cosmic web will still stretch across the sky. The questions will still be waiting to be asked. But for now, rest. We have talked about numbers so large they defy comprehension. We have traced the history of how our estimates changed, from thinking there were a few 100 billion galaxies to realizing there might be 10 times that many. We have explored the cosmic web, the filaments and voids and clusters that give structure to everything. We have contemplated the hidden majority, all those small, faint galaxies that our instruments cannot yet detect. We have talked about the tools we use, the telescopes floating in space and perched on mountaintops, gathering light from across the cosmos. We have talked about what makes each galaxy unique, about mergers and evolution, about the question of whether we are alone, and through it all, we have circled around a simple truth. The universe is larger, older, and more complex than we can truly comprehend, but we can still know it. We can still study it. We can still be amazed by it. That seems like enough for one night. The sky is dark now, filled with points of light. Each one is a star in our own galaxy, close enough that its light reaches us individually. Beyond them, too faint to see without telescopes, are the galaxies. Let your eyes close. Let your breathing slow. Let the numbers fade into abstraction. Approximately 2 trillion galaxies. 93 billion light-years. 90% hidden. Billions of years past, and billions more to come. And you, here, now, a brief arrangement of atoms that can think about all of this. The universe does not care whether you understand it. The galaxies will continue their slow spin whether anyone is watching or not. The cosmic web will stretch and thin regardless of observers. Stars will be born and die. Planets will form and be destroyed, and all of it will happen without concern for human knowledge. But you can know that is something. That is remarkable. In a universe that operates by blind physical law, with no built-in purpose or meaning, you exist as a pocket of awareness. You can wonder, you can question, you can count galaxies that are billions of light years away. Sleep now, beneath approximately 2 trillion galaxies. Dream of spirals and ellipticals, of filaments and voids, of light traveling for billions of years to reach eyes that can see it. Tomorrow, the universe will still be there. The questions will still be there. The wonder will still be there. But for tonight, rest. You have traveled far enough. Good night.